My name is Josh Ost, and I'm the Executive Director of Internet Security Research Group, or ISRG. ISRG is a nonprofit that was founded to serve as a home for public benefit infrastructure. We like to run digital services that improve privacy and security for everyone. We're probably best known for Let's Encrypt, our certificate authority. Today, Let's Encrypt is helping more than 260 million websites enable TLS to protect their visitors and themselves. We also do some other things, though, and today I want to talk about our memory safety initiative. Since our inception, we've been thinking a lot about how to run secure digital infrastructure. One of the biggest problems we have is the frequency and severity of vulnerabilities that are found in the internet's most critical applications. Most of these vulnerabilities are what we call memory safety vulnerabilities. The interesting thing about this type of vulnerability is that we know how to eliminate it. We could, with some considerable effort, make memory safety vulnerabilities a thing of the past. We just need to do the work. I'm not going to get into the details of what memory safety means today, but at a high level, a memory-safe language manages memory properly for programmers. Languages that are not memory-safe depend on programmers to manage memory correctly. When memory isn't managed properly, mistakes can lead to security vulnerabilities. Since even the best programmers frequently make mistakes, programs written in languages that aren't memory-safe are much more likely to have serious security flaws. When we talk about languages that are not memory safe in the context of internet infrastructure, we're mostly talking about C and C++. So the software that we use on the internet is relatively unsafe from top to bottom because of how widespread use of C and C++ is. So at the top, the closest to users, we have web browsers, which are typically many millions of lines of C and C++. From there, we have servers, more millions of lines, proxies, business logic, cryptography, image processing, and kernels. Pretty much everybody's running out of the Linux kernel or the Windows kernel. Again, millions of lines of C. So almost every deployment stack at every company and organization contains a ton of C and C++ code all throughout the stack. The vulnerability situation has gotten a little out of control. So Google estimates that 90% of Android vulnerabilities are due to a lack of memory safety. Microsoft estimates that 70% of all vulnerabilities in their products over the last decade have been caused by a lack of memory safety. And whenever you look at lists of 0 days or patch notes and things like that, a huge percentage of the vulnerabilities are due to memory safety. So society pays the price for this every day. It's privacy violations, financial losses, denial of service, human rights impact. These vulnerabilities have a real impact on people's lives and our society. So if we're going to have C and C++ code around, and we will for at least a long while, we should do our best to make it as safe as possible. And fuzzing and static analysis can help with that. So there are a lot of great efforts out there to put together tools that make C and C++ code safer. And that's fantastic. But they introduce a lot of overhead. They're sort of applied inconsistently. And ultimately, they don't solve the problem. So these are really worthwhile investments, but it's not what ISRG is focused on. We're trying to work on a more complete long-term solution. So we know how to solve this problem. That's what makes it so frustrating. Like I said, so many vulnerabilities are due to memory safety, and it's not like it's a problem we don't know how to solve. It's just a lot of work. We have to replace the code that isn't memory safe with code that is memory safe. We know how to do it. We have the tools. So let's get to work. And even if it takes us 5, 10, even if it's 15 or 20 years, the internet is not going anywhere. We have a long time horizon for these kinds of big investments to pay off. ISRG's Memory Safety Initiative has 2 goals. The first goal is to move the internet software infrastructure to memory safe code. The second one is to change the way people think about memory safety. We view our role as consisting of the following parts. We want to come up with a strategy. We want to help facilitate and coordinate the execution on that strategy. We want to help raise the funds for the people to support the people who are doing the work. And we want to help communicate about what we're doing and the problem space in general. So our engineers may do some of the work, but mainly we'll be enabling community and maintainers to do the work. The first part of our approach is to identify projects that have the best return on investment potential. So we're looking for projects that are very widely used. We're looking for projects that are particularly security sensitive. An example of something we think about there is what's sitting on the network edge? What's the most exposed to the world? So on the efficiency side, we're looking for projects where we can replace key components with existing memory-safe libraries. So when we can do that, it means that we don't have to write a bunch of new code from scratch. We can just swap out some old code for some new code or some other code. And we're also looking for maintainer and project cooperation. It makes it so much easier when you can get maintainers on board with a plan. So this brings us to slide number 2, which is we want to work with maintainers whenever possible. Maintainers have really valuable knowledge about their software and the people who use it, but they also have the ability to ship memory safety updates to existing users. If you can't get a maintainer on board and you can't change software that already exists, you have to build competing software and get users to switch to the safer version. That is much more difficult. We would so much prefer to work with existing maintainers and then be able to ship updates directly to users without them having to do anything except run the update processes that they should already be running. So in order to do that, part of what we need to do is find funding for maintainers. It helps us create buy-in and lets them know that we appreciate their time and their effort and alleviates resource concerns. And we're making a big ask here. We're asking them to introduce new languages into their software and change how components of it work in pretty considerable ways. So it's only fair that we help support them when they do that. The third thing I want to point out is that we really prefer a modular approach. It usually doesn't make sense to go out and rewrite an entire piece of software in a different language that's memory safe. We'd much prefer to do it piece by piece. So we want to encourage projects to replace libraries or module functionality with memory-safe libraries rather than ground-up rewrites. It breaks it up into manageable pieces and allows us to deliver value incrementally. So if we can just swap out one library for another and deliver that by a software update, we can sometimes do that in a matter of months. If we were rewriting the program from scratch, we wouldn't get that kind of incremental value. We might have to wait, 1, 5, 10 years, who knows. Also, when we have a modular approach, we can focus on investing in libraries that many different pieces of software can use. And when we improve those libraries, it improves lots of different software. Over time, we want to build trust with maintainers by building up a series of success stories. So it's, when I talk to maintainers, it's totally understandable to me that they have a lot of questions and concerns about what it means to start moving to memory-safe code. And part of convincing them that they can and should do this is showing them a series of success stories and say, here's a previous maintainer that had similar concerns to you. Here's how we talked through them. Here's the solutions we came up with. And hopefully this makes other people feel more comfortable with moving forward. So I'm going to talk about some of the projects that we're currently working on. The first project on the list here, and the first project that we embarked on, is Kernel. And I'm just so happy with how this turned out. So we identified Kernel as a really popular networking tool and library. It's in cars, it's in microwaves, it's on desktop computers, servers, it's all over the place. And it's a network tool, so it's on the network edge dealing with untrusted data quite often. And it has a really great maintainer. So we reached out to a guy named Daniel Stenberg who maintains Kernel, and he had a bunch of questions and concerns about what moving to memory-safe code might involve. They were really great questions, but he was open to listening, and we did a lot of listening too. And we worked together to come up with a plan that would not be disruptive to the existing users of Kernel, but that would add an option to use memory-safe networking code. And then maybe someday that code becomes default when it's well enough tested, but people will still have the option to use the old code if for whatever reason they're not able to switch. So we came up with a plan that was non-disruptive. We were able to find financial support for Daniel's work. And this has just turned out really well. It's such a great success story and has really helped to make other maintainers more comfortable once we explained how this worked. The next thing I want to talk about here is Russells. So Russells is a TLS library. We're essentially trying to build it up to be a suitable replacement for OpenSSL in many applications. So when we first learned about Russells, it was already a really excellent TLS library. And we have identified some things that can be improved. And then we talked to the maintainers about how we might do that, and found the funding to help make some changes. So Russell's is just getting better every day. We're really excited about it, and I think going forward, one of the first things we're going to be able to do in a lot of critical networking applications is move to a memory safe TLS library, and that library will often be Russell's. The next thing on the list here is a perfect example of that. So Apache's HTTPD is a really popular web server, and it has a module called mod SSL that provides TLS services to the web server. So we're working on a replacement module for mod SSL, and we call it mod TLS. And the new module uses Russell's for TLS. So when you switch to mod TLS, you get a bit more modernized TLS module that uses a largely memory-safe TLS backend. The last thing on the list here is the Linux kernel. It's very exciting to me that this is on the list at all, because when I started working on this project, I'm a pretty ambitious person who's willing to undertake big projects. But even I thought, the Linux kernel just might be too much. It was hard for me to imagine how we might make progress in bringing memory-safe code into the Linux kernel. Then I learned about some work that Alex Gaynor and Miguel Ojeda had been doing, and it was so impressive. They figured out how to build certain to build modules in the Linux kernel in Rust. So primarily we're thinking about drivers here, but someday it could be other parts of the Linux kernel. They had written a lot of the code. They managed to get really great feedback from the Linux kernel community. It's just so impressive to watch what these two have done, and we're really excited to support them. So that was a lot of information about how we plan to actually move code, but I also mentioned that we want to change the way people think about memory safety. So we're going to be doing a lot of communication about this problem. Fundamentally, if you ask an engineer today to deploy, let's say, for example, a reverse proxy, even a security conscious engineer might reach for something like Nginx or Apache or something like that. That's just millions of lines of C. That's standard practice. And I think a lot of people, either don't have a choice or don't feel that they have a choice about the tools here. But either way, I don't think we think often enough about the risks involved in putting millions of lines of C or C++ code on the edge of our network and processing untrusted network data. We have decades of evidence that, if you got a million lines of C, you are definitely going to have vulnerabilities. So I'd like us to think more clearly about what it means to be making that choice every day and get to the point where we fully appreciate the risks associated with doing this, and we start really investing in alternatives. So thanks for listening today. I want to make sure to thank Paul Kerr and Alex Gaynor for their work to bring dimension to this problem. My meetings with them and talking to them have been so helpful to me to understand, what are the problems that people are facing today, what's going to help move the needle in terms of how people think about these problems. I also want to thank Daniel Stenberg, Stefan Eising, Dirk Achman, and Miguel Ojeda for taking the first steps to really help start writing code and moving our infrastructure forward. And I also want to thank our funders, including Google, for understanding our vision and helping to make it a reality. And for understanding that open source maintainers need to be supported. Thanks so much.